So far what we have done is we've sort of writing this equation abstractly. Okay. So we'll take a quick look at a 1D problem. Okay. So this 1D problem, we'll take the wave equation. Okay. So the wave equation we all know is simply del squared u plus k squared u is equal to 0. Okay. And this is a 1D equation. So this is simply okay. So right now we won't go into actually solving the system of equations, because I want to tell you a little bit, give you an example of a boundary condition. So far we have not spoken about boundary conditions, right. So this is a 1D problem, that means the wave is going like this along the x direction, right. So let's take a coordinate system over here, right. So x, and let's make this y and z. Okay. And I am going to say that electric field is along the y axis, right. So which way, if the wave is traveling along x, we will take h to be along which direction? Z, right, your right hand curl rule, right. So E cross H is giving me the direction in which the wave is moving. Okay. So E I am going to take as my variable over here. So u of u at y hat. Okay. Fine. We already know what a plane wave looks like, right. So can I, without any detailed calculations, write down the form of h? There is a relation between the magnitude of E and the magnitude of h, right. There is a eta, impedance of free space, right. So ux divided by eta, which is impedance of free space, 377 ohms or whatever, square root of mu by epsilon, whatever, yeah, z hat, right. So this is my E, this is my h. Okay. Now there is another way of writing this, which is another way of getting E. I mean the original way of getting h was what? Take curl of E, right. And when I take curl of E, I should get minus j omega mu h, right. So when I simplify this equation over here, del cross E, there is only one term that survives, which is a z hat du by dx. I am just simplifying this curl expression. Okay. There is only one term that will survive, which is this, and this is equal to minus j omega mu, and h is ux by eta along z hat. Okay. This is simple 1D wave equation, we all know how to solve it, right. So from here what can we write? We can see it is all along z hat, so we can convert it into a scalar equation. What do you get? dux by dx is equal to, all of these constants I can write as j omega mu by eta ux. Okay. Agree? Nothing very complicated here. We didn't even need to know anything about FEM or anything over here. So if I ask you, where all is this equation valid? It is valid everywhere. Take any point x, this equation should be valid, because basically it is giving me the relation between E and H, right. If you look at the basic meaning of this equation is that the ratio of E to H should be eta, that is all. Now this actually turns out to be a boundary condition, because let us say that I want to get a wave equation, the solution to the wave equation, now not in free space, but I have a, let us say, a block of glass over here. My wave is traveling like this. Some of it will get reflected, some of it will go through, multiple reflections will happen, something will come out. And I want to solve this numerically, right. And so what I will say, okay, I will make this the ends of my computational domain. Now this equation that I have written over here, it should be valid at this point also and at this point also, right. So this is in fact the boundary condition on yeah, it's a boundary condition. I should not write boundary condition on boundary, it is a boundary condition, right. Now, you have seen so far in previous courses, you have seen Dirichlet boundary conditions. What do Dirichlet boundary conditions say? What is a Dirichlet boundary condition?
It is constant.
Constant, right. So, u of x endpoint is equal to, let us say x naught is equal to constant, right. What is the other boundary condition? Neumann. What is that? Derivative is constant. At the endpoints, okay. So, at x naught. What does this boundary condition look like? Is it Dirichlet? Is it Neumann? If you want, you can rewrite this as d by dx ux plus j omega mu eta ux is equal to 0 at boundary. Is it a Neumann boundary condition? Neumann boundary conditions would mean that this term is constant, but this, if I can also call it a Dirichlet boundary condition, because if I look at this term. So, in fact, this is neither of the two. This is a third kind of boundary condition. It's called a Robin boundary condition. Some people call it a, another set of people call it an impedance boundary condition, and another set of people will call it a yeah, okay, there are many names, Sommerfield, some people call it radiation boundary, and so on. Every community rediscovers this boundary condition and gives their name to it. Okay, so the circuits people call it impedance boundary condition, scattering people call it radiation boundary condition. But the idea is, because you have a linear combination of the function and its derivative being set to 0, right. So, in general, what is it? It's alpha u prime plus beta u is equal to constant. This is the kind of boundary condition that we have. Okay. So, you notice, if you recall over here, this in the weak form, the endpoints term has a du by dx, right. That is why this is going to be useful. I will substitute this du by dx in terms of this other term over here, and we will see how it leads to simplifications. So, when we will continue subsequently with trying to solve this equation using the FEM framework. Okay. Clear so far?